Okay, so I think it's recording now. Okay, so hello everyone. This is a book I've been working on since about August last year to help capture some of my ideas in case I might forget them in the future or in case someone else might claim them. Right, so I've started this book in the 27th of August 2022 on a Saturday. So this first one is me practicing an algorithm. It's really hard to aim with the camera weight. Practicing that algorithm to calculate square roots by hand, and this is, as far as I know, one of the ways that computers might do it. At first, I did try and use a binomial expansion type thing, but that did end up being a little bit too complicated. Okay, so this next one is which ad is that? This one. There. Okay, so this next one is a sort of function I came up with called a gap function, and the logic is you input a sequence in terms of the nth term, and I'll give you the nth term of the gaps within that sequence. So for example, I put the triangular numbers, which I derived this formula myself. Put the triangular numbers into here, and reason that logically, the gap function would just be n. Right, because let me aim this. Because 0 to 1 is going to be 1, 1 to 3 is going to be 2, 3 to 6 is going to be 3, by definition of triangle numbers. Then I decided to put in Fibonacci numbers at the bottom there. And Fibonacci numbers are a bit harder, but it is pretty easy to prove that the gap function of the Fibonacci numbers is the Fibonacci numbers. Exercise for the reader. Okay, this next page is a page where I sort of proved a very small bit of Fermat's last theorem. So, as a recap, Fermat's last theorem states that if you have an equation x to the n plus a to the n plus b to the n plus c to the n, where n is an integer that's greater than 2, then there are no integer solutions for a, b, and c. And I proved there are no integer solutions for a, b, and c when n is 3 and a minus b is 1. Which side's that? That's going back. Wait. What's this page? Okay, this page is me trying to prove that 1/2 factorial is square root of pi on 2. I kind of failed on that. I think I come back to it later in the book though. What's this page? Okay, this page is me practicing simultaneous equations to sort of see how you would take a list of 3 points and find a quadratic that goes through them. Using simultaneous equations. What's this one? Okay, so these next few pages, so this one is calculating the square root of I. And here I proved that the square root of I is either 1 over root 2 plus 1 over root 2i, or negative 1 over root 2, or negative 1 over root 2i, which makes sense because there will be a positive and negative square root. This side here, I did not prove this. This is Euler's doing, and it's essentially just something cool that I've learned. Over here I worked out a general formula for the xith root of I, and I proved that it's e to the pi over 2. Wait. Yeah, e to the power of pi divided by 2x. This one is just a list of identities that comes from Euler's formula e to the I theta equals sine theta plus I cosine theta. So cosine theta plus I sine theta. And here I work out what Here I work out what I to the power of I is, and I prove that it's e to negative pi on 2. and generalize that and say e to the power of xi equals e to the power of negative pi x on 2. Next page. What's this one? Okay, here I worked out a general formula for the nth root of x and showed that the nth root of x is e to the power of the natural log of x divided by n. What other ones are there? Here I proved the differential of e to the x equals e to the x by pretty early on actually, factoring out an e to the x here and bringing it out. It's really hard to aim it this way. Bringing out the e to the x and then proving that what was left in the limit must equal 1. And over here is proof of the quadratic formula, which is actually the same one I've put on my YouTube channel recently. This next one is me trying to derive the cubic formula by trying to reduce the cubic down to what's it called? Quadratic. But in the end, I reduced it into a quadratic, but there were roots with x inside of it, so I decided to check an awful lot for where it actually was, and found out that there's no way I could have derived any of these. Here I work out that 1 over I is equal to negative I, and the square root of xi equals e to the I pi plus 2 times the natural log of x divided by 2. And over here I decided to experiment a little bit by checking what roots of different order would give you for approximations of pi. So square root of 10 would give you 2 digits, 3.1. Cube root of 31 would be better, 3.141. The fourth root of 97 is actually a little bit worse, it's 3.1. And the fifth root of 306 is the best so far, 3.1415. And I think I came up with a conjecture that with higher order roots in general, the limit as the root order of the root goes to infinity will equal pi. Okay, so here I proved that the sum of consecutive odd numbers equals square numbers in a geometrical way and an algebraic way. And here's me trying to come up with an approximation or infinite series for pi. What else is there? Okay, so that infinite series for pi I had before, this is just me trying to make it super efficient. But while it does make it converge a lot faster, it can mean that you need an ungodly amount of computing power to actually make it work. What else? Here I proved that the golden ratio is the most irrational number that's least well approximated by rational number. What else? this is just me completing that Fermat proof from before by showing that the function that I derived at the beginning of the book doesn't have a root, doesn't have a 0 in the real axis. What else? Here I proved that the ith root of -1 is actually e to the power of pi, which I think is quite cool. Here I derive the number of possible combinations on a Rubik's Cube by reasoning about where you can put the edges and how many of those edge cases are reachable with standard moves. And here I come up with a new type of prime based off a Numberphile video actually about left and right truncatable primes. And at the end they asked about what about primes that don't matter if you what order you move the digits. So I decided to investigate that, and I called them widely truncatable primes, and I've proven that the only widely truncatable primes are 73, 37, that the biggest widely truncatable prime is 73, and the ones I found are 73, 37, and then all the one-digit primes, 7, 5, 3, 2, and also 23 and 53, which I'm pretty sure are all of them, but I haven't actually checked. But I've proven that 73 is the biggest one. This is me learning about matrices and how you can use them to solve simultaneous equations for the first time, which was pretty cool. This is a really long-winded proof to show that 2 minus 1 must equal 1. And here I actually prove I think it's Gaussian integral. It does take a while, but eventually I find that the integral from -infinity to infinity of e to the negative x squared must equal the square root of pi. And that indirectly proves the gamma function from earlier on in the book. Exercise for the reader if you want to do that. Here I prove that the 1 minus 1 plus 1 minus 1 plus 1 minus 1 all the way up to infinity, or the sum up to infinity of -1 to the power of n, as n goes from 0 to infinity, must equal 1/2, which honestly breaks my mind. This is me learning and describing algorithm for to calculate what day of the week it is. It's the doomsday algorithm, if you're curious. And here's me proving here's me proving the gamma function from earlier on in the book, which so here I'm is it? Wait. Yeah, this is me proving the gamma function from earlier on in the book. I think I forgot to put the square root of pi in there, and I just said pi on 2. And here's me developing a way to integrate over complex intervals and distances. So the way I defined it was that you work out the indefinite integral and then you do the bounds to begin with, and you find a function that will map onto the complex plane what you want to measure. And then what you do is you find the differential of that function, multiply it by the indefinite integral of what is inside the integral to begin with, and then you put the bounds on as real numbers as the real part of the complex number that you want to integrate over. This is proof that e to the power of I theta must have an absolute value of 1, I think. And here I make a general set of equations to find solutions to x to the power of y equals y to the power of x. And here I work out that the radius between two disks put perpendicular to each other. Wait, how do I aim this? Yeah, the radius between two disks put perpendicular to each other must be the square root of 2 for them to roll perfectly. And I'm not sure what this conjecture is. And here I derive the equation for time dilation in special relativity. General relativity, I'll have no chance. Yeah, here I prove that the absolute value of I to the x must equal 1. And wait, what do I prove earlier on then? Wait. Oh, here I make a conversion between I to the power of x and e to the I theta. Essentially, I work out what angle what angle it should make depending on what power you raise I to. What else? Oh, sorry, wait. I said you multiply by the differential, you multiply it by 1 plus the differential squared and then square root it all. Because Pythagoras. And here I calculate the mass of the Earth using the fact that general gravity must equal roughly 9.8, and using Newton's universal law of gravitation to work backwards to the mass of the Earth was. Here's a few repeats. Here I prove that 69 is the only number where the square and the cube have all the digits in base 10 repeated once and only once by an exhaustive search until the square and the cube together have 11 digits, which means that you'd have to repeat a pigeonhole principle. Oh, and here, now let me get that closer. Here I prove that 1 equals 2. Challenge the person watching to find their mistake. Don't put it in the comments. I want people to work out for themselves. What else? Oh, here I derived a formula for the nth digit of a number in a certain base, and reasoned that to prove that pi is a normal number, then show that this works for all integer values of n and d. Here I prove that the square root of 2 is irrational, and here I point out that 11 plus 2 and 12 plus 1 both have, oh wait, wrong side. That 11 plus 2 and 12 plus 1 both have the same 13 letters and are anagrams of each other. This is a proof of Pythagorean theorem. And what is this, just a repeat of before? Yeah, this is This is just a repeat of before as well. Here I prove that infinite nestled square roots must equal. Here I prove that infinite nestled square roots must also equal the golden ratio. And over here I prove Euler's formula with use of Taylor series. And here I generalize the proof for root 2 earlier, so that it generalizes to all primes. And here I prove the honeycomb conjecture, saying that a hexagon must be the best possible shape. Here I reason that it's already been determined that irregular patterns or complex patterns do not fit the criteria, and so that you're left with either a square, a triangle, or hexagonal packing. And I reason that triangular packing is the same as a hexagonal packing, but you can remove the 6 inner lines to turn it into hexagonal packing rather than a triangular packing. And here I essentially say, okay, if you make the square and the hexagon with the same area, which will have more surface area, which will have more perimeter, and I prove that the square has more perimeter, and so the hexagon is the best packing for a 2D surface. And here I prove that 0.9 recurring must equal 1. Wait, wrong side. Must equal 1 there. In 2 different ways. Did I do 3 different ways? No. And here I exercise the fact that every number can be written as the sum of 3 different palindromes. So here I take my birthday and split it into 3 different palindromes. Here is an attempted proof that there is no perfect cuboid. Annoyingly, I made a mistake pretty early on about here. Yeah, I've labeled it. And since then, I worked on it for about a month before I decided to take a break and come back to it later. It's a lot harder than expected, but here I come up with the concept of a mechanical calculator. Using a certain formula, for example, force is mass times acceleration, or velocity is resistance times, the voltage is resistance times current, or the resistance, the total resistance is the sum of all the small resistance, and arguing that you could use things like that to do calculations. Would be pretty limited, but it could work. And then we have the Chishti conjecture, wrong way. Then we have the Chishti conjecture, which I think I put on this channel before as well, where I find that the recursive formula Tn plus 1 equals 2 to the power of Tn minus 1, where with the seed T0 equals 2, and we've already checked T0, T1, T2, T3, and they're all prime. The question is, does this primality continue to all outputs of this sequence? And here I prove that there is no values a and b such that a squared is a prime times b squared. And here I come up with the formula 2n plus 1 squared minus 1 divided by 8 equals n times n plus 1 divided by 2. I haven't actually managed to prove that, but n plus 1 divided by 2 is a formula for triangle numbers. And 2n plus 1 squared minus 1 divided by 8 is a formula that I came up with for triangle numbers a while back, way before I started this book actually. What else? Here I described the chaos game, which I put a few simulations up on my channel, and I mention how they come up. And here, that's actually interesting. I was doing a probability problem and came across this, where 1 take away 1 over n, and then you need to take the infinite product of that. And I showed that that infinite product must equal 0. What else? Oh wait, I'm almost at the end, wait. Here I show that this is the best rendering of the Mandelbrot set you'll ever see. Here I show that if this point on the Mandelbrot set between the main bulb, then there's the main bulb of the main bulb. So between the main bulb of the main bulb and the main bulb on that, I show that if that point is rational, then the Feigenbaum constant must also be rational. And yeah, that's it. That's all I've gotten through the book till now. So, as always, thanks for watching and see you later.